So up first, we have Nick Rioux from University of Pennsylvania. He is on the job market, so if you're hiring, keep that in mind. And he will be talking about functional meaning for parallel streaming. Go ahead and take it away.
Thank you, Alexa. I'm Nick Rioux. I'm finishing up my PhD at the University of Pennsylvania under Steve Zdancewic, and I'm going to talk about our efforts to design functional languages for deterministic parallelism. So we encounter two problems here that you've probably heard of before. They're very old. The first is that concurrency makes it very easy for nondeterminism to seep into our functional programs. And the second is that nondeterminism makes programs really hard to write, not to mention debug and reproduce errors. So the classic example is if you have two threads that want to write to the same spot in memory. Well, depending on how the scheduler interleaves these two threads, you might end up with different results. And of course, this isn't limited just to sort of programming with shared state. Many kinds of concurrent models of concurrency suffer from this problem. So with message passing, you end up with races between messages sent by different processes. And in a distributed system, it's 10 times worse. Messages could be reordered, and they could even be duplicated. So what we really want is a language that gives programmers freedom from the scheduler. We don't want them to have to think about how different threads might be interleaved as they write their programs. And that's what determinism would give us. How do we get that? Well, there's been a lot of work in this area. And there's one idea that seeps up and has come up a couple of different times in the literature. And this idea is that if we want to have shared state, we can restrict that shared state. So the data that's stored in the shared memory is some value that's an element of an algebraic semilattice. And the idea is that when you write to that shared state, the value that gets saved in memory is the least upper bound of the old value and the new value that was just written. And the nice thing about this is that it means that it doesn't matter what order your writes are applied in. Least upper bounds are commutative, so you get the same result either way. So lambda join is a functional language that we introduce in this paper that supports a notion of deterministic parallelism using this idea of semilattices and a first-class notion of streaming data. It's highly expressive, so it's an extension of the untyped call-by-value lambda calculus. And we integrate this idea about semilattices by noticing that the lattice theory that's behind these other approaches is very easy to integrate into sort of a domain theoretic framework. And the idea is that that gives us a sort of denotational semantics for a language, and we can go backwards and pull out the language from the math, and the language turns out to have some nice properties. Why do we want another approach? Deterministic parallelism has been studied for a really long time, going back at least to the 70s with Kahn process networks. And there's been a lot of work since then, too. So what's different? Well, we don't think that we have a solution yet that quite meets all of these criteria. First of all, we do want the guarantee of determinism, but we also want a language that's expressive. So it should be Turing complete, and it should support powerful abstractions that functional programming gives us. And it should be one unified language. We'd prefer not to have two different languages, like a sequential language and a parallel language, that have to talk to one another. And lastly, lambda join is really declarative. So programs very closely match specs in a way that resembles Datalog. And because lambda join is functional, we get equational reasoning principles, not just over single threads, but actually over entire parallel systems of processes. So let's look at some examples. Here's a really simple example. This is the evens function. It computes the infinite set of all even numbers. Now we're using Haskell notation here, but it's not Haskell, and the semantics are different in a couple ways. In particular, this is a strict language, like I mentioned before. So how does this definition work? Well, first of all, we have the singleton set containing 0 here. We say, well, 0 is an even number. We take that set and we union it with another set. But here, this operator is called join, and it's kind of overloaded. It works as union on sets, but it'll work differently on other types of data like functions or records. And it's not really just a union. It's really this sort of streaming parallel union. The idea is that as you're computing, it runs its arguments in parallel, and as those arguments stream results out, it takes them and it merges them somehow, and then outputs the result in real time. Then on the right hand of the join here, we have a little expression that tells us if a number n is even, well then n plus 2 should also be even. We do that by mapping plus 2 over the recursive call to evens. So here's the function map, which is very easy to define for sets here. We use this big join elimination form. This sort of means take the union of all of the singleton sets f of x for every x in the set x's. And so this gives us what we want. It computes the set of all even numbers. But it's a very strange function coming from the perspective of many other languages, because in most other languages, and including lazy languages like Haskell, this would actually be a meaningless infinite loop. Your evens is calling itself back at the same argument. It's not terminating. And in fact, this is an infinite loop, even in lambda join. But lambda join works on a different model of computation. Lambda join programs don't need to terminate to return a result. They can stream them out as they're still running. So lambda join programs are these long-lived computations that stream results out over time. And that means that termination doesn't affect the meaning of programs. It means that a non-terminating program might even be equivalent to a terminating one. As evens runs, it's going to output a bigger and bigger result over time. And this is a property that's true of all computations in the language. They all, in some sense, grow the longer you give them to run. But what does grow mean? Well, it means that they increases according to some partial order. And we call that partial order here the streaming order. For sets, you can think about that order as being the subset order. But for functions or for records, it might be something different, like some kind of pointwise order. And so we have this property that programs grow over time, and it's true of every program. And in order to maintain that, we need an invariant on all of the operations in our system, that they're all sort of monotone over this order. So we can have, for example, set union, but we can't have set complement. And that's a restriction that is pretty familiar in the distributed setting to programmers who use CRDTs, where grow-only sets are like a pretty fundamental data type. So lambda join is strict, like I mentioned before, and it also supports a type of infinite data. And that's weird in and of itself, because usually in functional programming, we use laziness to encode infinite data. And that is not what is going on here. Like I said, this is a strict language. So how do we combine these two ideas? Well, it turns out to work if you have a notion of pipeline parallelism built into the language, right? Or this notion of streaming, that functions are producing output as they receive input. We'll talk more about that when I talk about the semantics down the road. Right now I want to give you another example, which is a two-phase commit. This is a very basic distributed algorithm. The idea is that you have two peers who are trying to agree on some value, and you have a coordinator that's trying to help them. The coordinator is going to propose some value to the two peers. Each peer will look at the value and decide whether it wants to accept or whether it's going to reject. And then when and if both peers have accepted, the coordinator should commit the result and indicate success. So here's the program. I'm going to explain it bit by bit. The idea here is we are in the streaming setting, right? So the first result that is computed by the system is bottom, and that's just sort of by fiat. Bottom here just indicates a program that has not produced any results yet. The entry point to the system is this system function in the bottom left, and we compute it iteratively. So like I said, in sort of iteration 0, the answer is bottom. But to compute the next iteration, what you have to do is you run the function here. But anytime there's a recursive call, you replace that recursive call with the value of the function that you got from the prior iteration. So the idea here is the last iteration was bottom, so now we're going to be passing bottom to the peers and the coordinator. And then the whole system or all three nodes become bottom. And so in the first iteration, the result is this empty record. In the next iteration, we do the same thing, but now the peers and the coordinator are getting past this empty record. And the peers get a chance to run, right? But the peers accept a record that has some field proposal in them. And so they're not actually able to run yet. The idea is they block until they get an input that they actually want, and empty record doesn't give them enough information to run yet. So they're bottom. But the coordinator does get to run, at least partially. The coordinator runs by producing this singleton record that maps the field proposal to the value 5. And so the state of the whole system now can be seen to be this singleton record, proposal equals 5. And that means that in the next iteration, the peers are now going to see this proposal. So the peers see the proposal, and in this case, they both accept the proposal, and they do that by returning a singleton record mapping OK1 or OK2 to true. And then all of these values, both from the peers and from the coordinator, get combined using join to compute the final result of this system. And so join is going to sort of concatenate these records into one here. And lastly, we have one more step to go, right? The coordinator at this point needs to see the results that came back from the peers. It's going to do that. It's going to look up OK1 and OK2 in the system state. It's going to combine them using logical and then it's going to apply this display result function to compute that to a string. And what we get in the end is that the system has accepted. It has a record field res that is set equal to accepted. So what are we really seeing here? Well, the key idea here is that lambda join makes it really easy to write these iterative fixed point computations. It's very Datalog-esque, but it's sort of dropping a lot of the restrictions of Datalog. We're in a full functional language, can do things like recursion, can work with higher order functions, and all of that. These computations are deterministic, and they're also very naturally parallelized. And they can express basic distributed algorithms like two-phase commit. What else is it good for? Well, even if you're not interested in parallelism or distributed systems, this model of programming can be useful because it gives you a way of dealing with infinite and cyclic data in a purely functional and declarative approach. So you can see the paper for an example of dealing with cyclic graphs. And this could be applied in the future potentially to, for example, static analyses that do iterative fixed point computations, to parsers. And since we handle infinite data and pipeline parallelism, it could even model string processing. Let's look at the semantics. The first way that we give semantics to this language, we give a semantics called an approximate operational semantics. The goal here is to describe how computations evolve over time. But how can this work, right? So the big problem we face is that is this combination of strict data with potentially infinite data. So here we're trying to call this contains function, which asks, is the number 4 in the set of all even numbers? And of course, the answer should be true. 4 is even, and evens is defined correctly. So it should be the case. But because evens is infinite, and this is a call by value language, evens will never run down to a value. And so contains, in theory, might never get to run. So in order to handle problems like this, we need to integrate pipeline parallelism. In other words, we need functions to be able to start evaluating even when they only have a part of their input. Functions need to be able to work with just partial inputs. And the way that we model this in our operational semantics is that a running program might non-deterministically stop at any given time. And if it does that, it just sort of returns a value that is the approximation of its full meaning. And so this sort of is a clairvoyant kind of non-determinism. In this example, you can see that evens stops after it's produced the first 3 results here, 0, 2, and 4. And that's good because that's all contains really needs. Contains doesn't need a full infinite set to produce the correct answer. It just needs to see the part of the input that contains 4. But this leaves us with a few more questions to answer. First of all, I've said that evens represents an infinite set, but how can I even justify that? Right? Operational semantics only tell us what's happened over a finite amount of time. So they can only really produce a finite amount of output. That's not great for infinite terms like evens. And the other downside is, like, in what sense is this deterministic? I started off the talk saying we want to do deterministic parallelism, and then our semantics seems to use nondeterminism. Well, the nondeterminism is really a trick for getting a cleaner specification. It's not really saying something fundamental about the language. What do we have to prove in order to demonstrate that? Well, you might think that we have to prove some kind of confluence property on a rewriting system, but actually confluence is trivial here. Bottom approximates all terms, so all terms step to bottom. Instead, what we do is we build a denotational semantics. We describe what a program means in the limit as time goes to infinity. That's what the denotational semantics will let us talk about. In order to do that, we use a technique called a filter model. Filter models are basically a way of defining a denotational semantics by defining a type system. We prove a computational adequacy result using a logical relation. And this lets us describe the behavior of terms in the limit as time goes to infinity. And it also lets us define the notion of determinism that we care about, which is that every term has one behavior in the infinite limit. So for people interested in domain theory, there's one kind of interesting tidbit that falls out of this. We solve the domain equation that represents lambda join, and when we do that, we find that sets in this language are denoted using what's called a Hoare power domain. But there's something new here, because sets are eliminated using this big join elimination form that I showed at the beginning of the talk. And it turns out combining these two things, sets denoted by this power domain and sets that are eliminated using this big join form, are surprisingly hard to prove adequate. And so we have a logical relation definition that is tricky and not at all what we expected at the beginning of this project. So take a look if you're interested in that kind of thing. There are a few avenues of future work that we're really interested in. One, we'd really like to be able to support for larger scale distributed systems more than just two-phase commit. And to do that, you really need to be able to handle non-monotone behavior in certain cases. So for example, you might have a key value store that clients can send updates to. And they should be able to update the key value store in arbitrary ways, not just sort of inflationary ones. So luckily, this problem's already been solved in the distributed programming community, and there's languages like Bloom that integrate this really well. And so we talk about in the paper how we can integrate ideas from those languages into this setting. And this is a problem that also needs to be solved if we ever want to be able to support sort of more advanced algorithms like distributed consensus algorithms. We also are really interested in supporting incremental evaluation. When I showed you the two-phase commit example, we sort of reevaluated the whole system at every time step. And you don't really want to do that. For real, you want to be able to work with sort of only differences, right? You want to be able to compute the difference in output at each time step. So we think ideas from semi-naive evaluation are useful there. And then we also really want aggregation in this setting, right? So we'd like to be able to express algorithms like PageRank using aggregation, and we'd also like to be able to write distributed quorums where you want to be able to count the votes that are shared between a set of nodes. So in sum, lambda join integrates ideas from a lot of different areas: functional programming, data log, parallel programming. And if you're interested in any one of these areas, you might be interested in looking at the paper to see what you could learn from the others. Thank you. And I am on the job market, so please feel free to come talk to me. If you have any positions open, my email's on the side. Thanks.
Okay, any questions for the speaker? Do I have student volunteers to run? Looks like there are 2 questions here.
Hi, I'm Jenga Lee from KAIST. First off, thanks for the talk. So as I understand, if you have an infinite computation, but you only need finite time to get the actual answer, then your semantics can find the answer. But what happens if you really need an infinite case? So for example, what happens on contains 3 even in your semantics?
Contains, we can't return false, so contains can never return false. It can only sort of return true when the element is in the set, or just essentially block otherwise. And that's a limitation of monotonicity in the language, right? You can't check for the absence of an element in a set. Just like I mentioned, you can't compute complements of a set.
Thank you.
Thank you for great work. It seems like the fixed point computations can be quite long, and it is going to do some redundant computations. So I wonder if you are having some primitives for scheduling so that these computations for this can be somehow efficiently executed without redundancies, or, yeah. So in short, do you have any scheduling constructs to execute this program fast?
So you want some kind of like hints to the scheduler to help it out and tell it what a good schedule would look like? Yeah, I mean, I think the biggest issue in terms of efficiency here is the incremental problem that I mentioned before, is that there's just a lot of repeated computation. And we'd like to be able to do that, to work just sort of with differences over time. We haven't looked at sort of primitives to talk to the scheduler, in particular because we're actually kind of more interested in distributed computation, which is something I thought a little bit more about.
Hi, Max New, University of Michigan. So you did an untyped language. Was that just an arbitrary choice? You could have just as easily done it as a typed language, or is it you need something like data funds type system for lattices and things like that?
Yeah, so the type, you can build a type system, but the type system is kind of non-trivial. So the issue here is that typical type systems sort of stop you from not producing any information. Like they stop you from trying to access a field on a record that doesn't exist. But there's a second problem in this language, that you might produce too much information. Like you might try to join true with false, and those things have no least upper bound. And so the type system that you would need to prevent that kind of error is different from from most type systems. And so that's still kind of an ongoing research problem. So it's easier to start with an untyped language first.
And you can do that in your language, like false or true?
If you do that in this language, you will get an error. It will be a runtime error.
I see.
And that's the good thing about that is it's deterministic. You will deterministically get an error. But yeah, you definitely want a type system eventually to prevent those kinds of errors.
Okay, thank you.
All right. And with that, let's thank the speaker again.